important Fourier transform pairs. Okay, pairs mean time domain signal and its Fourier transform in frequency domain. So this is the pair for each one of those. Okay, so we start by the most famous. So number one, the delta function, right? Okay, so delta of t. What's going to be the Fourier transform for this? Use the definition. The definition says that the Fourier transform of this signal is the integral from minus infinity to infinity, the signal itself, delta of t, x of t, my function as a function of time, multiplied by minus j omega t, and you integrate with respect to time. What's going to be the result of this?
J omega t.
When you integrate a delta multiplied by a function and you integrate from minus infinity to infinity, you take the function at
This point
0,
which is
right?
0, yeah.
So we take this function, this is the function multiplied by the delta, right? This is the function which is multiplied by the delta, right? So I take this function at t equals 0. So it becomes what? 1. So the Fourier transform is going to be a constant equal to 1, right? So basically the Fourier transform is e to the j omega multiplied by 0, which is equal to 1, right? So basically in time domain, I have this guy, right? This is as a function of time. In frequency domain, I have this guy. Versus frequency, I have a constant equal to 1 all the way from minus infinity to infinity, right? It's equal to 1 at any omega, right? That's what we got, right?
Yes.
And why does this make sense? Because the delta function is a very high speed changing function, right? So this means that it has all frequency components that you can think of, right? And it's happening at almost 0 time, which means that in frequency it will span all frequency range, okay? So that makes sense, okay?
Okay.
Physically it makes sense, right?
So it's 1 over like t and it's infinity, right?
Yeah, so, and at all frequencies, it occupies it has all frequency components. You have to, and we'll see later on that there is this duality concept that says that if something is very wide in time, then it's very narrow in frequency, and the other way around. If it's very narrow in frequency in time, then it's very wide in frequency, and that's what's happening. This is the narrowest possible, which means it's the widest possible in frequency domain, okay? So that's the first one. The second one is, second function is the rectangular function, rectangle of t divided by tau. And when we say rectangle of t divided by tau, we mean by this, okay, a pulse function, right, which is centered around 0. So it's a square function or a pulse function centered around 0, and it has a width equal to tau. So basically it starts here or it finishes here at tau over 2, and from the other side at minus tau over 2. Okay? And it has a height equal to 1. So that's a unit rectangle function. If we say rect of t only, then the width is from minus half to half. So the width is equal to 1. Rect of t divided by tau, then the width is equal to tau, and it's symmetric, so it's not shifted anywhere, right? Okay. So that's the rectangle function. This is very important because when you deal with most of the digital systems, you encounter such a pulse, right? When you have some digital data being transmitted, you typically send those digital data as constant values within a certain duration, right? Bit 1 is going to be a constant equal to 1, bit 0 is going to be a constant equal to 0, and so on, right? So this pulse is very important, and we need to know how it looks like in frequency domain. So what's going to be the Fourier transform of this? Okay. Now, this one is easy to calculate, but it's a little bit involved, so you have to do like further calculations. So let's look at it. So it's the integral from minus infinity to infinity, this rectangle function, right? T over tau, okay? And then multiplied by e to the minus j omega t dt, right? And this is equal to what? Again, the rectangle exists only from minus tau over 2 up to tau over 2. So my integral should be only from, because before that and after that, I'm multiplying 0 with the e to the minus j, right? So that's a 0 integral. So I only need to integrate from minus tau over 2 up to tau over 2, right? So basically, it becomes the integral from minus tau over 2 up to tau over 2, which is the pulse width, okay? And then within that range, what's the value of that rectangle function? It's equal to 1. So 1, right? Then 1 multiplied by e to the minus j omega t, and then you integrate with respect to time. Can I solve this integral? Yes, I can. This is going to be equal to what? Upper limit. So again, number 1, you have to do what? You are integrating with respect to time, so you have to do minus 1 over j omega, right? And then this is multiplied by e to the minus j omega, right? T, and the limits are tau over 2, and the lower limit is minus tau over 2. Okay? Then substitute, what will you get?
You have e to the power of negative j omega tau over 2.
Minus e to the, one of them is positive and one of them is negative, right? So if we flip them and get rid of the negative term, we have 1 over j omega multiplied by e to the j omega tau over 2 minus e to the minus j omega tau over 2. Correct? Everyone agrees? Okay. Now, two complex exponentials with the same phase, right? But one of them is positive and the other is negative and subtracted from each other. This reminds us with the sine function, right? But it has to be divided by 1 over 2j, right? You remember the sine function, so sine of x is equal to 1 over 2j e to the jx minus e to the minus jx, right? This is the definition of the sine wave from the Euler's formula, right? Yeah. So this is how you get the sine wave, right? So if I look at this, I have all the elements that I need except for the 2, right? So again, multiply 2 up and down. So you will end up with, in this case, this is equal to 2 over omega multiplied by 1 over 2j. This is multiplied by e to the j omega tau over 2 minus e to the minus j omega tau over 2, right? And this whole part, I can write it as sine of what? لا ما فيش j بقى. Sine omega tau over 2, right? And then I ended up outside by 2 over omega. The famous function of sine of something divided by the same thing, right? There is something called the sinc function. Sinc of x is equal to the sine of x divided by x. Okay, so I want to convert this into sinc. What should I do? I have to multiply this by tau, right? And take the 2 down there, right? So I multiply tau up and down, correct?
Yes.
Okay, so I stay the same value, and then I end up with what? Tau multiplied by 1 over omega tau over 2, right? And then the 1 up there is multiplied by the sine, so I would say sine omega tau over 2. So now I end up with what? Sine x divided by x, where x in this case is omega tau over 2, right? So I can write this as tau sinc of omega tau over 2. And that's the final expression for the Fourier transform of the rectangular function. So if I have a rectangle of width tau and centered, so the typical rectangle is not shifted or anything, then in frequency domain this looks like tau sinc of omega tau divided by 2. خلاص يا جماعة? Don't forget that tau here is just a constant. It's the width of the rectangular function. It's not a time variable. خلاص? The only variable here is omega. This is a function of frequency. تمام? And if you look at this in frequency domain, if you look at this guy in frequency domain, it looks like this. I think you already know the sinc function. It looks like this. Okay. So it's symmetric, and it looks like a main loop with a magnitude. So sinc of x will have a magnitude equal to 1 at 0, and then it drops down, and it reaches here 0 when the sine reaches the first 0, right? other than at 0 point, right? At 0 point, it's not equal to 0 because it becomes sine 0 divided by 0, and then you apply L'Hopital, you will find that it's equal to 1, okay? But then at the next value where the sine is equal to 0 is going to be when omega tau divided by 2 is equal to what? When is the next 0 of the sine? When omega tau divided by 2 is equal to? Pi. Sine pi over 2 is equal to 1. Sine pi is equal to 0. So when this point, right, is basically, if this is my omega, my frequency, so this point is going to be such that omega tau divided by 2 is equal to pi. So this point should be what? In terms of omega. Omega tau divided by 2 is equal to pi. This tells me that omega is equal to 2 pi over tau. And this is my first 0. 2 pi over tau. And the same from the negative side, it's minus 2 pi over tau. Okay? This is going to be the points of... Why do we care about these 2 points? Because again, if I want to figure out, eventually we discuss something called the bandwidth. You remember the bandwidth?
Yeah,
okay? So if I want to look at this signal extends up to infinity, right? It keeps on decaying and vibrating, right, up to infinity, right? But then the most important part of the whole signal is only this part. This is the part that contains really most of the energy of the signal, right? So I can practically ignore all the others and say that typically it occupies in frequency this range, from minus 2 pi over tau up to 2 pi over tau, okay? And that's gonna be the practical bandwidth of this signal. This is gonna be how much it occupies in frequency domain practically. The remaining ones are very small and I can ignore them. Assume that it gets there and then just disappears. Even though it stays, but this is gonna cause a very small error in my calculations. It's not a big deal, okay? So that's why I really care about where is the first point it meets the 0, okay? That's why I did extra effort to find out these points. Yes?
Is the bandwidth is the maximum frequency minus the smallest of...
بس ده theoretical. If you apply this here, it's gonna be from infinity to minus infinity. كل اللي أنا عمال أشرحه ده عشان أقول إنه for this case we are gonna ignore all the low amplitude parts, and then the maximum frequency is gonna be this guy, and the minimum frequency is gonna be this guy. Now, do you take the bandwidth from here up to 0 or from here to the negative? It depends. If you want to deal with complex signals, then both sides. If you want to deal with real signals, which is the practical case, then you only care about the positive side. So your bandwidth becomes only this part. Yes, from 0 to 2 pi over tau. Okay? Any other questions? Okay. So that's another important signal. The next one is, this is kind of, you will figure out how it looks like. So the signal, number 3, x of t is equal to 1, so constant in time. Okay? What do you think is going to be the Fourier transform of this one?
Something, sync maybe, no?
Constant totally, so it occupies all time. What's going to be the frequency? It's just a delta function. Right? So this in frequency is going to be delta of omega, but it will be scaled by a factor. So it's going to be 2 pi delta of omega. Okay? Now, how can you prove this? How can you prove this? Remember the previous ones, we derived them, right? Can you try to derive this from time domain? What will you have? If you try from the time domain and just apply the Fourier transform, what will you get? The integral from minus infinity to infinity 1 multiplied by e to the minus j omega t, and you integrate with respect to time. Can you solve this? You can't. After getting e to the minus j omega t outside, then you have to substitute infinity and minus infinity. What's the value of e to the j omega t at infinity? I don't know. Right? Because that's a complex exponential. So it's a cosine plus j sine. What's the value that we will take when t equals to infinity? I don't know. They might reach infinity at 0. They might reach infinity at peak. I don't know. I don't know where is the infinity, right? So I cannot solve this way. But you can do it the other way. So start from frequency domain, and then apply the inverse Fourier transform, right? So basically take this one which is x of omega, right? This is x of omega. And then try to move it to time, okay? In this case, x of t is equal to what? 1 over 2 pi, the integral from minus infinity to infinity, x of omega multiplied by e to the j omega t, and you integrate with respect to frequency, omega, right? Because we want to move to time domain. This is the inverse Fourier transform. Now what's x of omega? It's 2 pi delta of omega, right? So you can continue solving by saying this is equal to 1 over 2 pi integral from minus infinity to infinity, 2 pi delta of omega multiplied by e to the j omega t, and you integrate with respect to omega. And this is equal to, the 2 pi will disappear with the 2 pi, and then you have a delta multiplied by a function, then it's equal to the function at the delta. At omega equals 0, not at t equals 0, because we are integrating with respect to omega, right? So this is equal to e to the j 0 t, which is equal to 1. So we showed that when you start from this in frequency, you get to this in time. So this is enough proof that 1 has a Fourier transform equal to 2 pi multiplied by delta of omega. خلاص?
I have a question.
Yes.
How did they get this expression?
How did they figure out to prove it from frequency? Because of a property that we'll study later. Because when you look at the definition of the Fourier transform and the inverse, you will notice that there is very high similarity between how you move from time to frequency and how you move from frequency to time. This is put in a principle called the duality principle. So basically, if you know the Fourier transform of a particular signal, then that Fourier transform, if you put it in time, the frequency domain is going to be the time domain of the original one. I will show you that when we reach the duality principle, okay? So let's not jump ahead, okay? So this is how they figured out, and then you can provide this mathematical inverse proof, right? It works, okay? Another important signal, and we'll see later on why it's important, I'm not going to discuss it now, is the signal a to the j omega naught t. So a complex exponential in time domain with a particular frequency omega naught. So omega naught here is not my frequency variable. It's just a particular frequency value, right? Omega naught, okay? So what's the Fourier transform of this guy?
It will be like the one we did.
It will be like...
It will be this plus, or minus...
Again, if you try to get it from time domain, you will not be able to solve it. Because you will end up with e to the j omega minus omega naught multiplied by t, and then you solve that integral and try to substitute t at infinity and minus infinity, which is going to give you undetermined values, right? So this one, again, can be solved in the inverse way, but you need to know the solution. So the solution is going to be 2 pi delta of omega minus omega naught. So basically, shifted version of the constant, okay? And we'll see later on that there is one of the properties that says if you have any signal multiplied by e to the j omega naught t in time, this corresponds to the Fourier transform of the same signal, right? But shifted to omega naught in frequency, okay? And we'll see that later on. But anyways, for now, e to the j omega naught as a function in time, when you take the Fourier transform, it's 2 pi delta of omega minus omega naught. And I'm going to write in green here that the proof, okay, goes the same as number 3, right? Which is the 1. So you have to do it in the inverse way. Take this one and apply the inverse transform definition. You will be able to get the time domain e to the j omega naught t, okay? So that's the fourth signal. Just wait. Okay. So that's the fourth signal that we will discuss. And then after finishing this signal, we are going to move mainly to the properties of the Fourier transform. We'll study a few of those properties, okay? But before going to the properties, one last comment, and then I will take your question. The last comment is that only if I ask you to derive those, you will be required to do the derivation, because I showed you how to do the derivation, right? All these 4 signals, okay? Or the one that we solved as an example, the e to the minus at multiplied by unit step of t. Other than that, in most of the cases, you will actually have the list of all these famous Fourier transforms and some more given in a table, and then using the properties, you will be able to use those as well as the properties to figure out the Fourier or the inverse Fourier of a given function, okay? So you will not opt for the integral unless you are explicitly asked to do so. Otherwise, in most of the cases, in 99.999% of the cases, your solution is going to be through using the tables of famous Fourier transforms as well as the table of the properties. You do not need to memorize neither the properties nor the Fourier transform in terms of mathematical expression, okay? But you need to understand the properties and how to apply them, as well as how to utilize or use the table of the famous Fourier transforms, okay? So what's your question?
So is it true that if we do the Fourier transform of any constant, we'll get a delta?
Of any constant, yeah, it's a delta multiplied by the constant because of the first property, which is linearity. So if it's rather than being 1, it was some value a, then it's in frequency domain, it's going to be a 2 pi delta, okay? So it's just going to be scaled in frequency with the same value because the Fourier transform itself is a linear transformation. Okay, so no questions about those famous transforms and how you can drive them, and eventually what are typical questions, whether on the derivations or the typical ones that you will solve basically from the tables. Any questions about that topic? Okay, great. So we'll move now to the properties of the Fourier transform. And we will start, I'm not going to continue on the same page. I'd like to start from at least. So properties of Fourier transform. Okay. And the first property, okay, is linearity. Again, this is by definition. The Fourier transform is simply, you take the function, you multiply it by some complex exponential, and then you integrate. Now imagine you have the sum of two functions. What will happen? Each one of them, they were going to be added together, so each one of them can be separately put in an integral, right? Okay, and each one of those integrals is going to be the Fourier transform of each part, right? So, and similarly, if the function is multiplied by a constant, the constant will go outside the integral, so the whole Fourier transform will be multiplied by the same integral, right? Or same constant, sorry, okay? So linearity means, again, linearity has two parts, right? Homogeneously, homogeneous and additive, right? And putting both together, you can put them in one formula. If x of t has a Fourier transform x of omega, let's say x1, and x2 of t, has a Fourier transform which is x2 of omega, then then a x1 of t plus b x2 of t is going to have a Fourier transform which is basically a multiplied by the Fourier of the first plus b multiplied by the Fourier of the second. So by doing this, we combine both properties in one expression, the homogeneity and the additiveness, okay? But you can do them separately if you like. So you say if x1 has this and x2, then x1 plus x2 is going to give me x1 capital plus x2 capital, and a multiplied by x1 is going to give me a multiplied by x1 capital. You want to do it this way or that way? This is just a one-step expression, okay? So this is the linearity. And this tells you that, again, back to the question that was asked, if you know the Fourier transform, for example, of 1, then you know the Fourier transform of 2 and 5 and 10 and 15 and 100, right? All of these are going to be exactly the same in frequency domain multiplied by the same scaling factor, okay? So that's a very useful property. And again, if you know the Fourier transform, for example, so let's take a quick example on using this. For example, if I have the function z of t, which is equal to delta of t plus rectangle of t over tau, right? And then I ask you, what's the Fourier transform z of omega of this function? So find the Fourier transform, right? Then you will tell me, because of linearity, this Fourier transform is going to be the Fourier of the delta, right? Plus the Fourier of the rectangle. And each one of those is going to be in your famous table of transforms, right? You don't need to memorize it. It's going to be given to you in the table. So you will simply, again, you'll say because of linearity, because of linearity, right? And you write that the Fourier of Z, this is equal to the Fourier of Z, right? Of T, okay? Then this simply means that the Z of omega, which is the Fourier of Z of T, is equal to, what's the Fourier of delta of T? We said it's going to be 1, right? And the Fourier of the rectangle is going to be sinc, right, of omega tau over 2. And this is multiplied by tau, right? And then that's it. You found the Fourier transform of this without doing any integration, by simply looking at the table of the famous ones and applying the linearity property, right? And you're done, okay? Typically, this is how you will solve, but of course it will include more complicated properties. It's not gonna be like, this is the 1 plus 1 example. The other one is gonna be like the root to the this and raised to the power x and all these complicated stuff, okay? So the second property, okay, which is kind of not for the Fourier transform calculation, but it's important. Again, the bandwidth of a signal, okay? Ideally, you get the bandwidth by looking at x of omega, right, as a function of omega, and then seeing how much it spans, right? And this is going to be the bandwidth of the signal. Okay, so this is the ideal case. Okay? Typically, you look for, typically, or practically, okay, signals in frequency domain will not finish. Will always, so your practical x of omega will look something like this, for example, okay? It will never finish. It will just finish at infinity. So to get the bandwidth for this signal, there are several definitions, okay? There is the 3 dB bandwidth, which means that the value of the signal is reduced until it reaches half power, which means that the magnitude, don't forget that this x of omega is a magnitude, not a power, right? So which means that the magnitude is reduced to
root 2.
yeah, 1 over, so it's the magnitude multiplied by 1 over root 2, right? Which is like 0.707 or something? Yeah. Right, so basically you are looking for the point here where the value of this peak, okay, this is equal to approximately 0.707 multiplied by the peak, right? This is the half power bandwidth, and the half power bandwidth is going to be this width. Right? So you pick the point where the peak value is reduced to 1 over root 2. This is the peak multiplied by 0.707, which is basically 1 over root 2. Okay? So the peak multiplied by 1 over root 2, which is 0.707 of the peak value. It's going to be some value here. And then you draw the line. You take that. You drop it down here, right? And then the width from the 0 up to, so the width from, so you take the value here, you drop the line from that value, and then the width from 0 up to this point is going to be the half power or the 3 dB power, 3 dB bandwidth. We call that the half power or the 3 dB bandwidth, okay? There's another one that looks at 0.9 something, right? There are many definitions, okay? For the sinc function, we typically take, particularly for the sinc function, we typically take only the main loop. And then we ignore all the side loops, the smaller oscillations, right? We only take the main loop. So for the sinc function, special case, for sinc function, we only consider the bandwidth is going to be only the main loop bandwidth, okay? This is going to be my bandwidth, okay? So that's the second property, which is the bandwidth of a signal. It's always calculated from frequency domain. If the signal is finite in frequency domain, then you can get the ideal bandwidth, right? The theoretical bandwidth. If the signal is infinite, then you have to use some practical definition for the bandwidth. You cannot just assume that it goes to infinity unless it's something like the delta function, because that one never decays, right? So that one has an infinite bandwidth, really, okay? But it does not exist in real life. You cannot actually generate a delta function in real life. Okay, you can only approximate it, okay? Next, I know the lecture is a little bit filled, but okay. The time frequency duality. So time frequency duality. Sometimes they call this also symmetry property. Same thing. Okay? It says that if I have a signal in time domain f of t that has a Fourier transform capital F of omega, then if I have a time domain signal that looks like this one, so it's capital F but of t. So for example, this was a delta, then now it's a delta in time. Okay, so I had something in time that had a Fourier transform that looks like a delta. Now I'm looking for a delta in time, how it will look like in frequency. This is gonna be in frequency 2 pi f, this function form, but it becomes of minus omega. Okay? And I'll give you an example to show you how to apply it to one of the ones that we studied earlier. Okay? So this is how the duality is expressed. Let's see how we apply it. Okay? Let's take this nice example, which has to do with the rect function in time domain that corresponds to a sinc function in frequency domain, right? So we know that rect of t over tau has a Fourier transform, which is given by tau sinc omega tau divided by 2, right? Now what if I have a time domain function that looks like tau sinc, now rather than omega, it's gonna be t, right? Because it's a time domain function. Tau over 2. What if I have this and I'm looking for its Fourier transform? Then applying the rule, the Fourier transform, right, is gonna be a rectangle because it's f, right? But rather than being of t, it's gonna be of minus omega, and it's going to be multiplied by 2 pi. So simply, the Fourier transform of this, I can figure it out by looking at this guy, and it's going to look as a rectangle. And instead of being a function of t, it's going to be a function of minus omega. So a rectangle of minus omega divided by tau. It's the same function, only the t replaced by minus omega, right?
2 pi.
Yes, I didn't finish. Okay, that's why I left a space. Okay, and then that function is multiplied by 2 pi. Okay, so it becomes 2 pi. That's the frequency domain because this is a function of omega now, right? The frequency domain is 2 pi rectangle of omega divided by tau. Yes.
Should be a synchronized.
بدل sign ماشي. Sync. Okay. واللي فوق كمان. Sync. Okay. So that's how you apply the duality property. Okay.
So we are taking the same function but replace t with minus omega and multiply by 2 pi.
Yes. Because the time domain was the sinc function. احنا مش we're taking the sinc function, we're taking the rectangle function هنا. Okay. So because the time domain was the sinc function of t rather than being the sinc of omega, which was the frequency domain representation. Okay. So this allows you, if you know the Fourier transform of something, right, you can figure also the Fourier transform of its Fourier transform representation, right? Because this is the Fourier transform of this, right? Now this, using the duality, I was also able to figure out the Fourier transform if it was a time domain function, right? So this means that typically the table that you will get for famous Fourier transforms, you can also look at the frequency domain ones and think of them as being time domain, and using the duality you can get the frequency domain from the other column, right? So as if the table is being doubled, right? Got the idea? Okay, if you have the table, I'm gonna finish by this because I think we are already at the time limit. So if you have the table of Fourier transforms, typically you have time domain signals here, right? And you have frequency domain, the corresponding Fourier transform for each one, right? Okay. So you can think of this table as if it's being doubled, where in the extra extension, the time domain ones here are coming from this guy, right? And the frequency domain ones are coming from this guy when you apply the duality. So you just need to make sure it becomes minus omega instead of being t on this side, okay? So as if you have two of that table, okay? Which means that we can have a shorter table and applying this property. So the time scaling property says that if you have a signal in time domain, sorry, we call it x of t, and that signal has a Fourier transform, which is x of omega, then, so if this is the case, then if you scale x in terms of time scaling, so if you scale the time of x by a factor a, and again, if a is greater than 1, then this means compressing x of t. If a is less than 1, then this means expanding x of t, and if it's negative, it means in addition to compression or expansion, it's also time reversal, right? So if you do that to x of t, what you will get is that the Fourier transform is going to be scaled by, in terms of magnitude, by 1 over the absolute value of a. So regardless whether a is positive or negative, the scaling is always going to be positive in terms of the amplitude, and then the frequency is going to be inversely scaled. So it's omega over a, right? So if the signal was compressed in time, it will become expanding in frequency and vice versa. That's in terms of the width of the signal. In terms of the amplitude, it's always reduced by a factor 1 over the absolute value of a, okay? The most important part here is to notice this property, which actually has like a more generalized expression, which says that the time width, okay, of a signal multiplied by its bandwidth, okay, is always equal to a constant. Okay, so if you take the time width of a signal, how much duration it has in time, and you multiply that by the bandwidth, which is how much frequency it contains in frequency, that product, it's called the time frequency product or the time width bandwidth product, is always equal to a constant for any signal. Okay? So if you expand it in one domain, what will happen is that in the other domain, it will shrink. Okay? So the smaller the signal in one domain, the larger it is in the other domain. Okay? So that's the generalization of this property, which is the scaling. Now the other property is time shifting. Okay. Again, for these properties, you can always think that what happens in time, can happen in frequency, and then it's the dual of that, right? So if a signal is scaled in frequency by 1 over a, right, then in time it's multiplied by the amplitude absolute a, and it is scaled by a directly, right? So you can think of it the other way around, right? And this one does not need any duality or anything, just look at the equation, right? So you can always figure out if it's done in frequency, what happens in time domain. Now for the time shifting, again, if x of t has a Fourier transform, x of omega, then x of t minus some time shift t naught t minus some time shift t naught is going to have a Fourier transform which is exactly x of omega, but multiplied by a linear phase factor. So e to the minus j omega naught t. Okay? Sorry, omega t naught. Omega t naught. Okay? Now, why do I call this a linear phase shift factor?
Because it's constant.
First of all, this, if you want to get the amplitude of this signal compared to the amplitude of the previous signal, what's the difference between the two amplitudes?
It's the same.
So both signals, whether before time shifting or after time shifting, the magnitude is going to be, or the amplitude is going to be the same, right? Correct? Everyone knows that e to the minus j omega t naught has an amplitude equal to 1 or not? If you take the amplitude of this complex number, what's going to be the value? The magnitude is going to be equal to 1, right? Now what remains is the relation between the phase of this and the phase of this, right? So let's look at this. Let's look at x of omega on one side and e to the minus j omega t naught multiplied by x of omega on another side. Okay? So in terms of amplitude or magnitude, let's call it magnitude. So magnitude, okay? The magnitude for this one, right, is x of omega, right? It's the magnitude of that x of omega, whatever, as a complex number, you just get its magnitude and that's it. And the magnitude of the other one is also x of omega, right? Because it's x of omega multiplied by 1.
Yes.
It's the magnitude of this multiplied by the magnitude of this. But the magnitude of e to the minus j omega t naught is 1, right? So this has the same magnitude. What about the phase? The phase of this and the phase of that. So for this one, we call it the phase of x of omega. What about the other one? What's the phase for the other one? It's again the phase of x of omega, but what happens to it?
Subtract 2 pi t naught, or no, actually t naught over there.
T naught omega, right? So the phase here is the factor which is multiplied by j, right? E to the j something is e to the j phase, right? So it's a phase term only. And what's the phase here? It's minus omega t naught. So it's this minus omega t naught, right? Now if you plot this phase, versus frequency, and if you plot this phase versus frequency, so assuming that the phase of x of omega, for example, let's say it looks like this, okay? So you calculated it, you found it to be something like this, okay? Just some phase. So it's changing, for example, between pi over 2 and minus pi over 2, right? And this is the phase of x of omega, okay? What's gonna be the other phase? The phase of x of omega, this is the phase versus frequency omega, right?
Yes.
What's gonna be the phase of the other one, the red one?
So
The one
by t naught.
underlined by. So it will be added to it a line with negative slope, because this part is a straight line, right? Because as a function of omega, this is a straight line. It's a constant multiplied by omega. So it's a straight line with slope equal to minus t naught, right? So you will end up with something that looks approximately like this. Right? So let's put just dotted, and basically those squares are going to be on the dotted line. So they are tilted and shifted up. So they will look more or less like this. Right? Right? So the whole thing is going to be tilted. The whole graph is going to be tilted because you add a constant value, a linear value to it. So it will be the same graph, but the additions are going to be different from one point to the other according to the slope of the linear line, right? Okay? Now, the objective here was not to show you how the graph looks like. The objective was to show you that time shifting, so when we shifted in time, we ended up in the frequency with the signal, the same magnitude, so no change, but the phase of the signal has an added linear phase shift, okay? Linear because it's not constant. It's a function of omega, and it's a function of omega to the power 1, so it becomes a linear phase shift. خلاص يا جماعة? So time shifting basically in terms of effect results in frequency, linear phase shift. Okay? And we'll discuss this later on in terms of practicalities of systems and which systems are better than which in terms of how they affect the signals going through them. Yes?
Typically we use x omega or xf.
No, in the course here we will use x of omega. You can use x of f, but in this course we are fixed with x of omega. خلاص؟ لأنه the definitions when you use x of f as compared to x of omega, for example, in the inverse Fourier transform, you remove the 1 over 2 pi in the inverse integral, right? But here we are dealing with x of omega, right? If in some tutorials you are being taught through x of f, please notify your TAs, okay? We are using x of omega, so don't get confused. We are not working with x of f. خلاص؟ The next one is frequency shifting, which is, you can expect what's going to happen, right? So frequency shifting is going to look more or less using the duality like time shifting, but I'm going to write it because it's not as straightforward as this one. So there are slight changes, and it's only one change, so I'm going to do it anyways. So the other one is frequency shifting. Okay. So in this case, if you have x of t, which has a Fourier transform x of omega, then if I have x of omega minus some omega naught, this will correspond to a time domain signal, which is x of t multiplied by e, but instead of minus, it becomes plus, so e to the j omega naught t, right? So more or less, it's the same thing. The only difference is that shift in frequency does not produce a minus in the time linear phase shift, right? It just becomes omega naught t directly, okay? And the other one, it was t naught omega, but with a minus sign, okay? So that's the only difference between shifting in time and shifting in frequency. Okay. Next property is convolution product duality. So convolution, we put them again into two factors. So convolution in time. So if I have x of t, which has a Fourier transform x of omega, and I have another signal h of t, or maybe a system representation or whatever, that has a Fourier transform capital H of omega, then x, so this is the f part, then okay, x of t convolved with h of t is gonna change into product in frequency domain. So x of omega multiplied by h of omega. This is multiplication, no longer a convolution. So if you have two signals convolved in time domain, their Fourier transform is calculated by directly multiplying their individual Fourier transforms, right? So I know the Fourier for the first, I know the Fourier for the second, then to get the Fourier of the convolution, simply multiply the two Fouriers of the first and the second, okay? The other way around, multiplication in time, yeah. You can imagine it will result in a convolution in frequency, but just with a scaling factor. Multiplication in time. Right. Again, if I have x of t, which has a Fourier transform x, capital X of omega, and I have h of t, which has a Fourier transform capital H of omega, then if I have in time, okay, x of t multiplied by h of t, for some reason or the other, I'm multiplying two signals, or I have the time representation of a system in terms of the operation that it does rather than in terms of its impulse response, so whatever. So if I have to multiply those two signals in time, then this corresponds in the frequency in, again, a convolution, x of omega convolved with h of omega, with a scaling factor 1 over 2 pi. Okay, sorry, convolved. Okay, so you end up in frequency domain with x of omega convolved with h of omega, and then you scale the result by 1 over 2 pi. Okay, this is the correspondence, or this is the Fourier transform of the multiplication of two signals in time. Okay, now.
Would we have the case like where we have multiplication in like in time domain and like convolution and like frequency domain, and then we will say like we transform everything to time domain and then solve it and then return it again.
Why not? Yeah. It's up to you. Huh? Okay. Nothing that prevents this from happening. Is it practical or not? We will answer this later. Okay. Because it's gonna come in your assignment. Okay. The next property, okay, is differentiation in time. So time differentiation. And again, if you have x of t, which has a Fourier transform, capital X of omega, then okay, the nth derivative with respect to time, so if you take the nth derivative with respect to time of x of t, yarhamkumullah, okay, then the corresponding change in the frequency domain is going to be multiplication by j omega to the power n of the Fourier transform. Sorry, not capital F, capital X. Okay, so if, for example, I had x of t that had a certain x of omega, and then you are asked to find the Fourier transform of d by dt only, so the first derivative of x of t, then the corresponding Fourier transform is going to be the same Fourier transform multiplied by j omega to the power 1. So only multiplied by j omega, right? If it's second derivative, then it's multiplied by j omega times another j omega, and so on to the power n, okay? And don't forget that j to the power n is always going to alternate sign, right? So don't forget that, okay? Because j times j gives you minus 1, okay? Again, the other property is the time integration. Wait. If x of t has a Fourier transform which is x of omega, then, okay, if I integrate from minus infinity to some time value t, this is how you represent the indefinite integral, right? So if you integrate something indefinitely, like without limits, then the representation, or the unlimited integrals, okay, the representation in terms of integration with limits is going to be from minus infinity up to some time t, okay? So I integrate from minus infinity up to t. My signal, but again we'll use just a dummy variable, call it tau instead of t, because we put t already in the integration limit, okay? So if I integrate my signal in time domain, what happens in the frequency domain is a little bit complicated. So it becomes x of omega divided by j omega, which is, as you can see, that's the inverse of what happens when you differentiate, right?
Sure.
When you differentiate, you multiply by j omega. When you integrate, you divide by j omega plus some strange term, which is basically pi multiplied by x, which is the Fourier transform of x of t at 0, multiplied by a delta function at 0, right? So basically, added to the regular Fourier transform divided by j omega, you have a delta, you have an impulse at 0, right, in frequency domain, which is scaled by the value of the signal at 0 multiplied by pi, okay? The value of the signal at 0 frequency. The value of the Fourier at 0 multiplied by pi, okay? What's your question? You forgot. Good. That's the strategy. Okay. Last but not least, as an application, it's not really a property, but as an application to what we have mentioned, signals and linear time invariant systems, okay, in time and frequency, right? So we've learned before that, okay, if I have a system which is linear and time invariant, then I can represent this system by the impulse response, h of t, and I can use this with the convolution to calculate the output for any input. So I know that y of t in time domain is equal to the input to the system, x of t, convolved with the impulse response of the system, right? The corresponding in frequency domain is going to come from the convolution property, right? The output is equal, the output here in time domain is equal to the input in time domain convolved with the impulse response. Then it must be that the output in frequency domain is equal to the input in frequency multiplied by h in frequency, okay? And we call that h in frequency, we call it the transfer function of the system, which is the Fourier transform of the impulse response. So in frequency domain, again, my linear time invariant system is gonna have a transfer function, call it h of omega, and the input is gonna be the Fourier of the input, x of omega, and the output is gonna be the Fourier of the output in frequency domain y of omega, and the relation says that y of omega is equal to x of omega multiplied by h of omega, okay? Where the relation is x of t has the Fourier transform x of omega, y of t has a Fourier transform y of omega, and the impulse response h of t has a Fourier transform, which is the system transfer function h of omega, okay? So these x's, y's, and h's are related by simply taking the Fourier transform to go to the frequency domain. خلاص يا جماعة? So this allows us a very useful tool. If I have input to a system, and I have the impulse response, and I find that the calculation of the convolution is quite complicated, then I can take the whole thing into frequency domain, calculate the output, and if I need to look at the output in time domain, what should I do? Just inverse Fourier. So simply I will move the whole system to frequency, then calculate y of omega, and then if I need to calculate y of t, I will just take the inverse of y of omega, right? Which is typically going to be something from the tables or whatever, okay? So that is going to be, in many cases, much easier than convolution, because convolution does not have tables. You have to go do it graphically and calculate the integrals and do all these things, right? But the Fourier transform has nice setup for most of the common functions, where you can use the tables and the properties in order to calculate whatever you need without having to solve integrals, okay? Any questions, Shabab? Okay. So the last thing that we will discuss today, and then we will try to solve at least one problem, or maybe we can leave this to next time. Okay, I will leave this to next time, and I will try to solve with you one problem. So let's try a problem. For example, find the Fourier transform of x of t, which is equal to unit step of t multiplied by cosine 2 pi t.
We use the properties. The multiplication is the.
Okay. First of all, does this have a Fourier transform or not?
Yes,
Why?
because u of t has a Fourier transform. And the cosine t has.
So yeah, because this is kind of critical. If you look at it from the absolute integral point of view, so if you try to integrate this segment
It's not going to work.
from 0 to infinity, right? To figure, from minus infinity to infinity, to figure out whether the absolute integral is finite or not, you will not be able to determine what happens, right? Okay, so the other way is as you did. So just look at it, it's composed of two parts, and those two parts are, both of them you can find the Fourier transform for. So the way to find the Fourier transform is going to be to do what? Yeah, so you'll use two properties, right? Sorry, one property and the tables, okay? So anyone has the tables for Fourier transform? Anyone has the book? Anyone can get it from online? Anyone has anything?
I saw it online, but it's very big. I was very confused when I saw it.
The unit step?
No, the whole.
At the table?
Yeah.
No, no, it's only like a couple of pages. No, only a couple of pages. It's probably written with a big text. The one that you saw. Anyone has the table?
I'm downloading it right now.
So we want to do the following. Number one, find, right, u of t as a Fourier, right, from table. Okay. Number two, find Fourier transform of cosine 2 pi t from table. Right? Both of these are famous functions. You can find them from table. And then number three, apply the time multiplication property. Okay? So basically multiplication in time is going to result in convolution in frequency multiplied by 1 over 2 pi. So who has this one?
Pi
Unit step of t.
is equal to delta.
So u of t has a Fourier transform which is
Pi delta omega
pi delta of omega
plus 1 over j omega.
j omega. Okay? And then the cosine 2 pi t.
So pi and then like big brackets.
Hmm?
Delta omega minus omega naught.
Okay, so delta of omega minus, what's omega naught? 2 pi.
Yeah.
So delta of omega minus 2 pi.
Plus delta omega plus 2 pi.
Okay. And now what remains is to do the convolution. So you have to do the convolution of pi delta of omega plus 1 over j omega, right? This whole thing is convolved convolution مش multiplied. Convolved with ما احنا هنا مش هنحتاج الconvolution هنا does not really need the integration. We'll see why. Okay? Convolved with pi multiplied by delta of omega minus 2 pi plus delta of omega plus 2 pi. تمام? Now, what do we need to do? Number one, we can capitalize on the fact that convolution is distributive and convolution is linear. So if two things are added together, we can separate them and do the convolution separately on each one of them. And then if we convolve something with something plus something, then we can distribute the convolution, right? So basically this convolution can be calculated as pi delta of omega convolved with delta of omega minus 2 pi, and this is multiplied by another pi, right? Okay, and then added to it, right? Pi times pi delta of omega convolved with delta of omega plus 2 pi, right? And then added to it again pi times pi times 1 over j omega convolved with
No, there is no 2 pi's. Only 1 pi.
the other case does not have 2 pi's. So pi only
Yes.
convolved with تفضلوا pi only convolved with 1 over j omega convolved with delta of omega minus 2 pi, and then the last one is going to be pi over 1 j omega convolved with delta of omega plus 2 pi. In any case, when you have a signal convolved with a shifted delta, what's the result? The signal shifted at the location of the delta. So this is what we are going to do in each one of those. I'm going to leave it for you to write the final answer for this. خلاص? Given the property that when you convolve something with a shifted delta, you typically take the function and put it at the location of the delta. خلاص? So that's what's going to be